Greetings all. I don't know what time you're going to be watching this video, but I hope you take some time to reflect on this chapter. There's a lot of material here that is foundational for biology, foundational for physics, foundational for the earth sciences. Earlier, we covered some of this material on these next few pages. We talked about thermodynamics. Notice thermo, heat, dynamics, means the heat's doing something. It's going places. And we have some what we call laws of thermodynamics, which we study in this chapter, but which we apply in many of the other chapters. And you also hear about these laws of thermodynamics in physics and biology as well. They are some of the most fundamental laws in all of the universe. And engineers have to study thermodynamics very carefully because thermodynamics must be taken into consideration when you build machines and design buildings and fabricate all kinds of devices such as your calculator or your iPad or your smartphone. All of these things, you have to take thermodynamics into consideration. One of the most obvious applications is you always must make it possible to get rid of heat that always is produced when things happen, when machines work. Even if there aren't moving parts, there's always the generation of heat. And so we try to do two things. Number one, we try to reduce the amount of heat that is produced as much as possible. And number two, we try to design the device in such a way that it can shed that heat into the surroundings as easily as possible. The accumulation of heat is what causes many systems, be they steel girders all the way down to semiconductors, to fail. We also talked about the law of conservation of energy down here. And then the law of conservation of energy, as you might imagine, is something that you've heard about since grade school, that energy is neither created nor destroyed. It must be accounted for. And we talked about the philosophy behind that and how fundamental worldviews had to change in order for us to, first of all, realize that that is true, and second of all, then, to be able to make advances in thermodynamics, because now we're no longer assuming magic or mysterious interactions of gods doing strange things. We also said that any discussion of thermodynamics requires you to distinguish between the system and the surroundings. Sometimes we divide it even into three categories: the system, the immediate surroundings, and the rest of the universe. But for our purposes, most of the time, just considering the system and the surroundings is sufficient. You already know that when work goes from the surroundings into the system, we say that that is endothermic, and that is a positive change in heat. Another way of saying that is that the surroundings are doing work on the system. Or you can have heat going from the system to the surroundings, which actually is much, much more common in all kinds of systems, be they biological or physical. And that means that we give this a negative change in heat, because the system is losing energy to the surroundings. It had a certain amount of energy. Let's say it had this much energy, and now it loses it to the surroundings. And so it goes out into the surroundings, and now you have this much energy that's a little bit lower down on this graph. If this graph here is energy, you've gone down in energy because you've lost it to the surroundings. That's why we give it a negative sign. Now, what's going to be new in this chapter is we're going to start talking about doing work on the system. The surroundings can do work on the system, or the system can do work on the surroundings. And that's a fundamental physics principle that you might remember from when you took freshman physics. And once again, the signage, the plus and negative signs, are the same. When the surroundings does work on the system, it's kind of like saying work is going from the surroundings into the system, and that will be a positive value. When the system is doing work on the surroundings, then that would be a negative value. It's not really true that the system is losing work and the work is flowing into the surroundings like heat does, but for the sake of being consistent with the negative and positive signs, we can say that whenever work goes from the system to the surroundings, that's going to have a negative value. It's important to keep those two words in mind. Now, we mentioned also the directionality of heat. It's unidirectional, that unless you're doing work on something, heat will naturally go from warm to cold. Heat will naturally flow from where the highest temperature is to where the lowest temperature is, assuming that those two regions or areas or system and surroundings are in thermal contact, so that heat can move from one to the other. If there was an insulating barrier between the two, then it would be hard for heat to go from the hot to the cold. That, for example, is why we might have a thermos, an insulated thermos, or we might have insulated windows or insulated walls or a ceiling in a house to greatly slow down the flow of heat from hot to cold. That might be in the wintertime, we don't want the heat to exit the house and go into the cold surroundings. And in the summertime, we don't want the heat from the surroundings to come into our nice air-conditioned house. Now, we also mentioned that any time you have two things that are in thermal contact for long enough period of time, so that any sources of energy begin to dissipate and run out, eventually things in thermal contact will all have the same temperature. And we went over these bullet points as well. This is a spontaneous change to go from the hotter to the colder. You don't have to make it happen. In fact, you can't keep it from happening unless you do work on the system with an air conditioner or with a heat pump or a refrigerator. And so this is a spontaneous or natural occurrence. And in fact, we might even begin to say this is fundamental to the first law of thermodynamics. If the first law of thermodynamics is that energy is neither created nor destroyed, but must be accounted for as it goes from hot to cold, what we're actually presuming ahead of this first law is that heat naturally goes from hot to cold. And we could call that the zeroth law, the zero law of thermodynamics. Though the first law was stated long before they really articulated well that the first law depends upon the principle I just mentioned of heat going from hot to cold. We also mentioned that we don't really know what heat is, but we have concluded that it is one form of energy. And we talked a little bit about the history of this earlier in the week. We've mentioned the words exothermic and endothermic. You can see the prefixes. Exo means to exit. Endo means to enter. And those are fundamental vocabulary words in chemistry as well as in physics and engineering. Now we might ask ourselves this question: just how much heat is going to go from one place to another? Well, the amount of heat that goes from one place to another, you might recall we derived this equation intuitively, which means we thought about what is logical, and we said that the greater the temperature change something undergoes, the delta T, the greater the amount of heat something will have absorbed or lost. So if you have a steel ball that goes from 5 degrees to 10 degrees, it's gained a certain amount of heat. But if it goes from 5 degrees to 50 degrees, a bigger change in temperature, it will have absorbed a bigger amount of heat. So we can say that Q, the amount of heat, is directly proportional to the change in temperature. We also said that if you had an object of greater mass, if you had a 50-gram steel sphere compared to a 1-gram steel sphere, and they both underwent the same change in temperature, the object with the bigger mass will gain or lose more heat per change in temperature. In other words, those two quantities are proportional. Q, sorry about that, Q is proportional to the mass. And finally, we mentioned the fact that Q is also going to depend upon what kind of material we're talking about. And that's where this C comes in. C is the specific heat capacity. And different materials have different specific heat capacities because they have different molecular structures. And that makes a lot of sense. And then in order to not need a fourth constant in there, a proportionality constant, we incorporate our proportionality constant into C, so that now we can say that Q is also proportional to C. And when you put all three of those things together, since our proportionality constant is embedded in the specific heat, we have this very famous equation that you see before you. Let me erase all of that. And so we say Q equals MC delta T. Now remember that a change in temperature Celsius equals a change in temperature Kelvin. They are going to have the same changes because they have exactly the same number of degrees. There each has 100 degrees between freezing and boiling, for example. The only difference is you start in a different place with your numbering. You start with freezing water at 0 Celsius, but 0 on the Kelvin scale is that absolute 0, the lowest possible temperature that you can approach, where your kinetic energy of your particles approaches 0. So a change on the Celsius scale is the same as a change on the Kelvin scale. So therefore, your delta T, when you have that in your equation, means you don't have to convert temperatures that are in Kelvin into Celsius or vice versa. However, if you're in Fahrenheit, you would have to make a change. You would have to convert it into one or the other. And we also talked about the fact that we have different specific heats for different substances, and this is a very, very small listing. There are tables and tables online or in books of tables where this list is many, many pages long. And when you give your specific heat capacity, notice that you can do it in joules per gram. You can sometimes find a chart that might be in joules per kilogram, Kelvin, and sometimes you can have it in joules per mole. And of course, this is where you convert your grams into moles in order to get the molar heat capacity. The molar heat capacity, logically, is the heat capacity of a mole of whatever substance over here you're talking about. So you can convert back and forth between the specific heat capacity and the molar heat capacity as long as you know what the substance is so that you can find out what its molar mass is. And here's a solution of that problem, showing you the care that's being taken to use dimensional analysis to make sure that your grams are going to cancel. You're not in moles, you're not in kilograms, you're in grams. And this is going to mess some of you up on a homework problem, and hopefully not a test problem, if you don't pay attention to your dimensions. Those who do not pay attention to dimensions end up suffering dementia and get very frustrated and get the wrong answers. Another thing that you ought to notice is that your Kelvin scale right here, your Kelvin scale cancels out the Kelvin over here. But it could also be Celsius. And the only unit that's left, you'll notice, joules and joules. All right, moving down to page 214. Quantitative aspects of energy. You know qualitatively, because you can feel it, or maybe you can even observe some boiling or steam if it's hot enough. Qualitatively, you can observe sometimes a change in heat, but quantitatively means we want to measure the amount of heat that's gained or lost. Remember, it's extremely difficult, if not impossible in most situations, to measure the heat directly. So what we do is we measure the heat in terms of what does it do. When you change the amount of heat, it's going to produce a change. It might produce a change in temperature, or it might produce a change in state or phase. And that enables us to measure the total amount of heat. And so sometimes you have the heat causing lots of changes. For example, in this picture, down here, if we were to put a hot piece of metal into a beaker of cold water, you're going to have heat going from the hot metal into the cold water, which happens to be in thermal contact with the beaker. And so your metal is going to lose heat, and both the beaker and the water are going to gain heat. And if you wanted to make it even more complicated, you could talk about the surroundings outside of the beaker, which is why, because that's kind of complicated, we normally try to get some kind of insulating blanket and put it around the beaker, like a styrofoam cup or one of those foam containers that you can put a can of soda in to keep it cold, or a cup of cocoa in to keep it hot. And that way we can avoid the loss of heat to the surroundings when we do our mathematical determinations of heat gained and heat loss in a process which we call calorimetry. Now, you might wonder, where in the world did this word calorie come from? And this is several centuries ago. The calorie came from the word caloric. And caloric, C-A-L-O-R-I-C, was thought to be the substance that comprised heat. Heat was made out of caloric. And so the goal was, if you could capture this caloric and store it in a container, then anytime you needed some heat, you just pop the lid on the container, let a little bit of caloric out to warm things up, put the top back on again, and so forth. Well, now we know, of course, there's no such thing as caloric. So we're just going to erase that. And heat is a form of energy. But the word calorie, coming from caloric, as a measure of heat, persists. Now, most of the time, 99% of the time, in AP chemistry, we'll be measuring heat in joules, like we measure all the different kinds of energy, kinetic energy, potential energy, and so forth, in joules. A lot of times we'll be in kilojoules when we're talking about larger quantities. Very seldom are we going to use the word calorie. You might also remember that there's such a thing as a kilocalorie. A kilocalorie is 1,000 calories, which equals capital C-A-L. The capital C calorie is what you see on cereal boxes and energy bars, and fortunately they don't put it on Ted Drew's ice cream, because when you have Ted Drew's ice cream, it's a special occasion, so you do not want to think about calories then. But all foods, of course, you can talk about how many calories. So if you have a piece of chocolate cake and it's 70 capital C calories, that's actually 70,000 little c calories, which is 70 kilocalories. And not that that would keep Americans from eating copious quantities of calories. You might remember some of that from physics way back when. And so once again, any system, be it a physical change or a chemical change, everything that is at the higher temperature is going to be losing heat to anything that is at the lower temperature. So another way of stating the fact that heat energy is neither created nor destroyed, if it's flowing from one place to another, is to say that whatever is losing heat has to equal whatever is gaining heat. So if we use Q, again for heat, Q lost has to equal Q gained. So if I have a hot piece of metal losing heat, and I put it, because I'm going to put it in a beaker of water, then my heat gained is going to be the heat that I measure from MC delta T for the beaker and the MC delta T for the water. So sometimes you got to keep in mind that calorimeter, and sometimes some problems you're going to ignore that calorimeter. And that's what they're doing right here in this problem. They've got the Q equals MC delta T for the water, and they might have the Q equal MC delta T for the metal, and the Q equal MC delta T for the beaker, if that's important in the context of the problem. Now, another thing that heat can do besides causing a change in temperature is it can cause a change in state. And here we don't mean going from Missouri to Kansas. Here we mean a change in phase, going from solid to liquid or liquid to vapor, vapor to liquid, liquid to solid. And a change in phase, if you were going to go all the way from a solid at a very cold temperature, and here we're at a temperature lower than zero, and we're going to go to a temperature higher than zero, 100 degrees. In this case, we're looking at water. Notice that there are 5 parts to this graph. Here's part 1, here's part 2, part 3, part 4, part 5. I call this a 5-step problem. And you can peek over here and see your 5 steps. Now you'll notice that in 3 of the steps you have a change in temperature going on. So if I try to change color here on my pen, so you have a change in temperature going on right here, right there, and right there. So those changes in temperature are going to involve an MC delta T, an MC delta T, and an MC delta T. Now the mass, let's pretend we're not losing any water to spillage or to steam, but it's all captured, the mass would remain constant throughout this problem. However, the specific heat of ice is different than the specific heat of water, which is different than the specific heat of steam. You're going to find those specific heats in a chart. You won't have to memorize them. But you do need to remember they are different. They are not the same. Your change in temperature, of course, is how long does it take to go from -50 to 0. And then over here in number 3, you're going from 0 to 100. And then up here in number 5, you're going from 100, in this case, to 200 degrees. That's your delta T. Now, when we talk about the change in phase, you have two changes in phases, one there and one there. This change in phase right there is where you're going from solid to liquid. And by the way, you could also go backwards from liquid to solid, and that's called the heat of fusion. Sometimes you're going to see that as heat, F-U-S. Sometimes you might see it as delta heat, F-U-S. Sometimes you might see it as Q, F-U-S. Chemistry has a tendency to use delta H. Physicists have a tendency to use Q. I should also mention that this term fusion has nothing to do with nuclear fusion. This term was in the vocabulary long before we knew anything at all about what powered stars and about nuclear energy. It's an old-fashioned word that is stuck. It's like when you fuse molecules in a liquid state together, you get a solid. That's kind of where that word came from. Now we also have another change in state right there. There you're going from a liquid to a vapor or a vapor to a liquid. That's called the heat of vaporization. And it's the same amount of heat whether you're going from vapor to liquid or liquid to vapor. You just reverse the sign. If you're adding the heat, for example, if we're going this way, since we're adding heat to the system, that's positive. Those values are positive. If we were going the other direction, I'll draw it up here, that would be negative because you would be losing heat to the surroundings as you condense into a liquid and then freeze into a solid. Please notice that your heat of vaporization is much, much bigger than your heat of fusion. So, which leads us then to a very important illustration, which hopefully will save your life. Well, hopefully you will never be in the situation, but if you're walking down the street and you're accosted by Al-Qaeda, and they say, which would you rather have? Some boiling water thrown at you, or some steam, both at the same temperature, 100 degrees, thrown at you, which should you pick? Well, theoretically, you'd want the boiling water because the boiling steam has all of this additional heat that's been added. It's gone from, if you come over to the heat, it said all this additional heat's been added. Now, of course, when you throw water, it's all concentrated, so probably the water would do more damage. So I'm afraid I haven't helped you much if indeed you ever find yourself accosted by Al-Qaeda. And finally, this is an actual example of doing a calorimetry problem involving changes in temperature and changes in state. I call this a 5-step problem. Each of the 5 steps has a certain amount of heat involved. And as we go through here, you can see there's step 1. We're getting the ice up to 0, MC delta T. Step 2, we're melting the ice. We need the heat of fusion from the chart. Step 3, we're going from liquid at 0 all the way up to water at 100. MC delta T again. Step 4, we are taking our water at 100 and we're boiling it. We're turning it into steam. We need a heat of vaporization. Step 5, we're taking our steam, increasing its temperature so it's at MC delta T. Once you have those 5 steps, then you add them together to get your result. And I will tell you right now, you will get one of these on your test for Chapter 5. I'm going to stop right now, and hopefully that you found this helpful.